Hello, besties. We're going to go over Fall 2017 question 6 now, starting with 6A. So this question says, given the following function definitions, what is the worst case running time for a call to P with the input N? Assuming N is very large, right? And assume that in this case, H is a Boolean function requiring constant time. And we see H is referenced here. And so just looking at this problem from a high level, what we're going to see is that the end goal, what we want to analyze is P of N. But P relies on knowing how long R takes. And R, we see, has a call to S. And S, finally, only relies on S and H, which we know is constant. And so we see there's a sort of chain of events or chain of calls. And in order for us to analyze P, we first need to analyze S and R. And so we're going to start with S because it doesn't, this is sort of like the end of the chain, right? S only depends on H really, which we know is constant. And so we can analyze S first. And so if you'd like, you can pause the video right now and take a moment to think, what is the worst case behavior for S? Well, if we look at S, we see that there are two if statements. And the first one, we can assume we're not really going to enter right away, right? Because we assume the input is very big. K is going to be some big numbers, so we can't just assume that K is going to be less than 0. However, for the second statement, if H of K, this Boolean function is sort of almost like flipping a coin. It's up to chance, right? We don't really know what it could return. It could be true or false. All we know is that it takes constant time to evaluate. And so we see that if H of K is true, we would just return K and be done with the call. However, if it's false, we're going to make a recursive call over and over and over. And so we see that the best case is when H of K is always true and we just return right away. And the worst case, which is what we're analyzing here, looking for, is when H of K is always false. And so we always enter this recursive call. And so now that we know what the worst case is, right? The worst case is when we just do recursive calls over and over because this is false. What is the runtime for this worst case? So you can take a moment and think about that. And what we're going to see is that we essentially just have K recursive calls, right? And each one takes constant time. Specifically, if we start with an input of size N, for example, right? We're going to have a recursive call S of N, which takes constant time, then S of N minus 1, N minus 2, so on and so forth, until we finally reach 0. And each of these takes only constant time. And so the total work done in S is going to be N work or linear in the worst case, which is what we're analyzing. So we see S has a linear worst case. Now that we're done analyzing S, we can sort of go back up to R, which depends on S. And so what is the worst case behavior for R? Well, again, we see that there are basically two conditionals which result in us returning quickly. And then there's the option where we have recursive calls. And so again, similarly to S, we see that in the best case, you maybe enter this and you return quickly, whatever, and there's no recursive call. But in the worst case, we are recursing. And so if that is the case, how many recursive calls will we make? Well, we start with I being 0 and M being essentially N, right? And we're going to go until I is greater than or equal to M. And so basically we start at 0 and N, then we do a recursive call with 1 and N, then 2 and N, and we're going to go all the way until I is greater than or equal to M, or in other words, after N recursive calls. And so again, here we have N total recursive calls and how much work is done at each call. Well, in one call, we first analyze sort of just a comparison, which is constant. And then we have to analyze this S of I line, right? And we saw that in the worst case, S itself is linear. And so we're doing a linear amount of work on every call. So we have N calls, N recursive layers. At each layer, we do N work. And so the total work done here is n squared in the worst case again. And so finally, we're done analyzing R, and so we can return back up to P, and we see that the work done here is pretty much just what we figured out was the work for R, which is n squared. And so this is the answer for 6A. Now we can move on to 6B. And so this says, what's the worst case running time for the call P of n? Assume that calls to H, again, are constant. And so let's check out this function. We see that we have two variables, or yeah, two numbers L and U, which are at 0. We're going to go until U is less than, or while U is less than M, or N really is our input size. And we see that L increments by 1 and U increments by 2. So I'm almost thinking of L as like lower and U as upper maybe. And we see that there's an inner loop, which is essentially going to go from L to U times, right? We start at L, go all the way up to U, incrementing by 1, and it's constant within there. And so I'm going to use maybe how many times H is evaluated as sort of our metric of like a unit of work. And so let's count how many times this happens. Well, initially, L equals 0 and U equals 0, right, in the outer loop. And this means in the inner loop, we go from L to U, or in other words, the amount of work or the amount of times we evaluate H is the difference. And so U minus L equals 0 here. Then we increment, and so L gets incremented only by 1 and U gets incremented by 2. And the difference between these two, or in other words, the number of times H is evaluated, is now going to be 1. Okay, I'm trying to figure out if there's a pattern here, so I'm just going to keep going. Again, U gets incremented by 2. And now we see H gets evaluated 2 times. Okay, there's some sort of pattern emerging, right? Sorry, U is incremented by 2, so it's like this. And now the difference between them is 3. That's how many times we evaluate H. And we can keep doing this. And what we're going to see is that the amount of work done in the inner loop is 0, 1, 2, 3, 4. Okay. And when does it finally end? Well, it's going to end when U is equal to N, or almost equal, right? Like we're going to stop right before this point, which means L, which has been incrementing half as quickly, would be N over 2. And then the difference would be N over 2. And so this column right here represents all the work that we've been doing in the inner loop, or how many times H of I is getting evaluated. And we see it's approximately 1 plus 2 plus 3 plus 4 plus da 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 plus N over 2. And if you remember our special like sort of sums that we have been using a lot in this class, we recall that 1 plus 2 plus 3 plus 4 plus N minus 1 plus N is approximately N, or N work, right? It's bounded by N. Which means this is approximately N over 2 work. But in asymptotic analysis, we don't really care about multiplicative factors. And so in total, it does N work. Or sorry, I've been saying N. I meant to say N squared in all of these. Yeah, this sum adds up to N squared, right? The one that adds up to N is 1 plus 2 plus 4 plus 8, right? That is our other important sum. But this one adds up to N squared. And so we see that we're doing roughly N over 2 squared work, which is really just the same as N squared over 4, which is the same as N squared because we drop those multiplicative factors. And so the total work done here is N squared. Cool. Now we can move on to 6C. And so this question says, the version of Kruskal's algorithm discussed in lecture takes as input an unordered list of edges and uses a union find structure that performs union and find operations in very close to constant amortized time, processing the edges in order by edge weight to build the MST. Consider a modification of the problem in which the input consists of a red-black tree whose node labels are the edges, ordered by weight. Will this algorithm provide an asymptotic improvement to the previous or original algorithm? Explain why or why not in 2 to 3 sentences. And so really what this problem requires is an understanding of how Kruskal works. And in general, if I were to give you sort of the vibe check of Kruskal, like the overall, the quick rundown, what it does is it sorts all the edges in order, right? And then takes the lightest edge and says, hey, are the 2 things on either end of this edge already connected? Like, is it gonna make a cycle to add them? No? Okay, cool. You're in the MST now. And it goes and takes the next lightest edge and says, hey, if I add this edge, is it going to create a cycle? Is it going to connect 2 nodes that are already connected, right? That's where the union bind comes in. No? Okay. And he keeps going down the line, adding the next lightest edge over and over because we're trying to build an MST or use the lightest possible edges while still avoiding cycles, or in other words, connecting 2 things that are already connected. And so the modification we've made basically says, hey, now instead of just giving you, the straight up graph where you have to take all the edges and sort them, we're also we're giving you a red black tree with the edges. And so what we can do with this is that instead of having to sort all the edges at first, right? Like I said, Kruskal has to sort the edges and sorting takes n log n time. Now we can just do an in-order traversal of this red-black tree, because a red-black tree at the end of the day is just a binary search tree. And the in-order traversal, which is linear or n time, will give us the sorted edges. And so this is awesome. And now we no longer have that n log n sorting time, which was really the major time constraint on Kruskal's algorithm. And so this is 6C. Now we have 6D, and so it says, assume that f and g return positive values. Is f plus g in the set of all functions that are bounded by, like perfectly theta bounded by, the minimum between f and g? If so, show why. Otherwise, provide a counterexample, and to show that a formula E is in the set of theta f is true, using the definition of theta bounds, give appropriate values k to make k times f larger or smaller than e. And so what this question is basically saying is, if I have 2 different functions, f and g, or not necessarily different, but I guess 2 unique functions, f and g, is it true to say that the sum of those 2 functions is going to be bounded, upper bounded and lower bounded, by the minimum of either of those functions? And my thought is we should try to come up with a counterexample, because to me, my gut instinct is like, well, adding 2 things to me sounds like it could definitely be bigger than the smallest of the 2 things, right? And so let's think about, what if f was constant and g was in, I don't know, n squared, right? F of x is constant and g of x is in n squared. Well, then f plus g, so I'm gonna make this 1 actually. F plus g is going to be n squared plus this constant 1. But we know in asymptotic analysis, this is essentially just n squared because the biggest term drives it. However, the min between f and g is constant, right? If we're looking at f and g, where one of them is always 1 and the other one is n squared, it's going to be constant. And so now the question is f plus g in theta of the min? Or in other words, substituting in what we found, is n squared in theta of 1? And no, it is not, right? N squared is not upper bounded by constant. We can't say n squared is never going to grow faster than something that's constant. And you can see my little graph I've drawn here. No matter what we pick for our constant value, n squared will always cross it or grow bigger than it. And so n squared is not theta bounded by 1, which means this is false. And so we found a counterexample. Cool. Now moving on to 6e, it says, suppose that h is in constant time and k is a constant that is greater than 0. Let's say f is some function which is equal to this sum right here. And let's fill in the blank with the simplest and shortest expression we can find to summarize basically what bounds f. And so we're basically just trying to simplify this math expression as much as we can, and using like our asymptotic sort of like hand waviness to get rid of extra terms that we don't care about, right? And so what do we see? Well, h we said is constant, right? Which means this whole thing essentially just goes away because we can just replace it with 1. And so now what we have is the sum from I to k of n of j. Or in other words, we have, sorry, not I to k, 1 to k. So we have n to the 1 plus n to the 2 plus n to the 3 plus da 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 until we reach n to the k, right? This is the total sum for f. However, again, because we said we want to find the shortest expression we can find, and we're doing this like math simplification, we see that the biggest term is what drives the sort of runtime of f. Or in other words, we drop all lower order terms. And so really, this boils down to n to the k, right? F is in theta bound, n to the k. Cool, and that is e. And f builds off of, part f builds off of e, which says consider the function f as defined in the question above. But now suppose that h of n is greater than 0, but it's upper bounded by 1 rather than theta bounded by 1. So in other words, we're saying that 1 is an upper bound, but not necessarily a lower bound, or we could have better than constant in this like mathematical theoretical world, right? So give an example of such an h that the entire function is constant. In other words, we want it to be such that there's no other word. We just want this whole thing to be constant, right? And so in our original analysis, we said, oh, h, we're just going to replace it with 1 because that's the theta bound, right? Now we're saying it could be better than 1. And so if we want this whole thing to sort of cancel out, we should just make h sort of be the inverse, right? And so if h is now 1 over, if let's say h of n is 1 over n, what's going to happen in this sum? Well, then we essentially see that this expression turns into this, which is really just 1, right? N over j divided by n over j, or n to the j divided by n to the j is 1. And so now the total work done is a constant being added k times. Okay. We said that k is constant, which means the total work done, no matter what, is just going to be this constant k, because we're summing this constant 1 k times. And so we've achieved our goal of having f be constant time by setting h to be 1 over n, basically. Or if the term, if the reusage of the term n is confusing, just think h is some function that essentially takes the inverse of the input, the multiplicative inverse, the input divided 1 over the input. And so this essentially results in these terms canceling out, and we get our constant time f. And that is question 6.